Thank you very much, Bethan. So, hello everyone. I'm Arthur Pryor, Senior Research Engineer at the National Centre for Additive Manufacturing here in Coventry. So, if you haven't heard of us before, we are the UK's independent body supporting industry to adopt and mature additive manufacturing. Over the last 10 years, our team of 50 engineers has delivered more than 700 projects for companies of all sizes, so ranging from SMEs to some of the large OEMs. And we pride ourselves on being process and vendor agnostic. So what that means is that when you work with us, we can offer you an independent and unbiased source of information rather than promoting a specific machine or technology. So we can support organizations through the sort of complete process chain and adoption journey, starting with strategy, where we can help understand where AM makes sense and how to build a credible business case. From there, we can support organizations with their product and process development. So we can help you to select and also benchmark materials and technologies. We can run feasibility studies, design parts for AM, and help you really sort of optimize your processes. Finally, we can support businesses to then implement AM. So whether that would be through training, through facility planning, or qualification support. And for LFAM specifically, we can support organizations across the complete process chain to help them really overcome some of the challenges that they might encounter. So in this presentation, I'm just going to be talking about our work in these different areas. I'm going to focus particularly on the end-of-life recycling topic that you see here at the end. So in underpinning all of these capabilities is our state-of-the-art facility here in Coventry, where we offer open access to some leading-edge manufacturing equipment, and that's supported by a really wide range of testing capabilities. So our main R&D platform is our Seed FlexBot, which is sat here to my right-hand side. And this machine has a 6-meter cubic build volume and an E25 pellet extruder. And what I'm going to do later in this presentation is also share some really exciting updates about this cell. So if you'd like to learn more, we're going to actually share these two overview decks in the chat, and that way I can focus more on the technical stuff. So within the UK itself, we're really fortunate to have a really strong LFAM ecosystem. We've got some leading organizations providing hardware, software, materials, and research services. And this is also alongside a growing number of end users who are using this technology in both production and also pre-production R&D environments across a really wide range of applications. And what's interesting about this technology is that we're seeing it being used for both some really demanding applications, such as autoclave tooling, and even end-use applications like printed vessels, if you've been following this technology. And at the same time, because LFAM is quite cost competitive when commodity polymers can be used, we're also seeing it being used for some really low criticality applications. So things like patterns, trimming fixtures, molds, jigs, and even outdoor furniture. So this ability to sort of support both ends of the spectrum is due to the huge variety of thermoplastic materials that are available. And it's also thanks, I guess, to decades of knowledge and the mature supply chains that this technology has inherited from the plastics processing industry. So all of these applications, they're driven by the fact that LFAM as a technology offers the highest build rate and build volume of any additive manufacturing process. It's a highly automated process that lets you manufacture meter scale structures in a single build. And this obviously avoids the need for multi-part assemblies. And that's ultimately the reason why it can offer these significantly shorter lead times. Another key benefit, because it uses thermoplastics, the materials can also be recycled. However, the technology also comes with some challenges, and hopefully many of you in the room are aware of those challenges if you're already using the technology. So, the geometry of parts you can produce can be more constrained than with other AM processes. People with hands-on experience will know that managing warping and residual stress, dimensional stability can be a challenge sometimes. And also predicting part properties can be difficult because of the toolpath dependence, anisotropy, and fiber alignment, and some of the thermal expansion effects. So overall, it does require relatively high level of operator skill to get the best results from the technology. So as an example of the types of parts you can produce, as we've done with our machine here to the right, here we have a vacuum trim fixture. So this fixture would be used to trim a carbon fiber part after the layup process. It was manufactured using Airtech's Daltrum T100GF material, which is a recycled PETG based polymer. And this was produced in 33 hours, completely unattended. As you can see, lights out production. And after printing, it weighed around about 388 kilograms. So it was printed in its near net shape and then post-machined. Machining process took about 8 hours. And in this case, the programming and simulation were done using a commercially available software called Additive. So looking briefly at that software workflow, this slide highlights some of the techniques that are used when designing parts for LFAM. One really important principle is designing solid so that you can slice hollow. So unlike many other AM processes where you'll tend to see a lot of internal infill structures, those typically aren't used with LFAM, and instead parts are printed with quite thick perimeter walls, but using supporting ribs to provide stiffness where it's required. If anyone's joined this webinar wondering whether this technology would be a good fit for your application, then I'd really recommend carrying out a DFAM study using your own geometry, and ideally producing a demo part. And that's going to be the most direct way to determine whether this process will suit the geometry that you have in mind. One of the key benefits of thermoplastics is their ability to be recycled. And actually, interestingly, being a pellet-based technology, recycling is actually much easier than with FDM. So, the quality requirements for producing filament are much higher in that case, and pellets, tend to be much more forgiving feedstock. So at the MTC, we've been working on this topic for several years through projects funded by the Department for Energy Security and Net Zero, in collaboration with AI Build and WEIR. And so in this video that I'm going to show you on the left here, I just highlight some of the recycling processes that we've been testing here in the lab. So in this particular project, we're evaluating Airtech's T100GF material for a UK foundry who are producing large sand casting patterns with this material. So our experience is that if you control the recycling process correctly, then actually with some minor equipment modifications, you can print directly using regrind, meaning that you may not need to repelletize the material after granulation, as you can see here in this video. So in this case, a key goal of the project is really looking at how we can actually blend virgin material and regrind to really find the optimal refresh ratio needed to maintain, let's say, acceptable material properties. So the important concept here is the dilution effect. So if you add a fixed amount of virgin material each cycle, then the overall composition will gradually become dominated by older generations until it sort of reaches a steady state. So the example shown here is a 1:3 refresh ratio, so 25% virgin material. And as you can see on the right-hand side, this will reach an equilibrium after roughly 25 processing cycles. So in this test campaign, we're actually evaluating 5 different refresh ratios and comparing them with fully recycled material. And because we're working with thermoplastic composites, both the polymer matrix and the reinforcing fibers will, of course, degrade. And we're interested in tracking those changes through a combination of techniques, really. This includes mechanical testing, rheological measurements, fiber length analysis, gel permeation chromatography, and also a print quality assessment. So this slide just sort of illustrates the types of testing that we've been doing to really help companies understand the recycling process. And what I wanted to do was to just summarize some of the key takeaways from all of these projects. So number one, our experience has been that recycling is best suited to applications with, let's say, like a lower functional demand, where the traceability of the materials can really be controlled. So for example, if you're producing parts like patterns, jigs, or fixtures, and if you're using them in a house, then this scenario could be a good fit for you to recycle those end-of-life parts. It's also a process that's going to be more suitable for the, let's say, the low warp polymers, so materials like PETG, whereas you're going to generally struggle to be processing some of the more difficult materials, for instance, polypropylene, because of that reduced fiber length. Controlling particle size distribution is really important. So this requires, in our experience, the material to be sieved after shredding and granulation. And if you can control that particle size distribution, then printing directly using regrind is feasible with just some minor equipment modifications. So another point around fiber length. So fiber length, we found generally drops off quite dramatically after like the first 1 or 2 cycles. However, it then begins to actually stabilize and reaches this so-called unbreakable length. And so, yeah, the fibers by the end have more of like a kind of filler-like consistency. Because of those fibers, it makes they're quite abrasive, right? So on your recycling equipment, you're really going to want to be using cutting tools that have a hard coating. So for instance, something like Niploy or a similar surface treatment to prevent your equipment from wearing too much. So I've got some other points here. I'm not going to go through the whole list because we're going to share this presentation with you. So you will have my top 10 key takeaways from our recycling projects at the end of this presentation. And I just wanted to conclude this presentation by just sharing some really exciting news about what we're going to be up to in 2026. And that will involve some really exciting expansions to our LFAM capability here, which will include integrating a DEMEX system from Lean. So we're really happy to have Patrick here to tell us about this technology, along with a new data logging system, extruder, and also a new controller. So these upgrades are intended to help our partners to work more effectively with some of the high temperature polymers, and also to support end use applications where we think that quality assurance and in-process monitoring are going to become really important. So we're super grateful to Lean, Siemens, and also Seed for partnering with us on this. And I'm also really pleased to share that Seed will be joining the MTC as an official member in 2026. So if any of this aligns with your development plans, then please do get in touch, because at the minute we're actively scoping collaboration opportunities starting this year. If you are interested in working with us, there's generally three ways you can do this, either through a one-to-one project with us, a collaborative R&D program funded by UK government, or for example, the EU, or by joining the MTC as a member. So if you'd like to discuss a project or just chat about an idea, please do get in touch. So I'm going to hand over to our next speaker now, which will be Thomas Hadrava from AirTech. So thank you very much.